Welcome to this video lecture on stability studies. Stability studies are carried out in order to set expiry dates for drug products. Drug products, even if they're stored correctly, can degrade over time. And so, after a certain period of time, the drugs have degraded to a degree that renders them unfit for use. Usually this is determined by taking the claim on the label. So let's say we have a 500 milligram paracetamol tablet. So the claim on the label says that it contains 500 milligrams. So when the drug degrades so that the active pharmaceutical ingredient content falls down below 90% of that quantity, which in that case would be 450 milligrams, we often take that 90% figure as a threshold to determine the shelf life of the product. But when the active pharmaceutical ingredient degrades to below 90% of the label claim, that's the point at which the expiry date should be set. The way we do this is we test the drug product at different time points. We carry out an assay at 0 months, when the drug is just newly manufactured, again at 3 months, 6, 9, 12, 18, 24, 36 and 48 months. So we carry out these assays in order to get some information on the rate at which the drug is degrading. We then carry out a regression of assay on time. So we are expecting a linear decrease over time in the percentage of active pharmaceutical ingredient as measured by the assay. So time goes on the x-axis and the assay percent goes on the y-axis, and we're expecting to see a line that decreases in height from left to right. So when the regression line falls below the 90% threshold, this suggests to us a suitable shelf life so that we can set an expiry date. Now, it's worth noting that the regression line, as always, represents the average y for a given x. So it represents the average percentage of pharmaceutical ingredient. So at that point where the regression line crosses the 90% threshold, we would expect that at that time, half the doses exceed 90% and half the doses are less than 90%. Because different batches can behave differently, we typically take 3 batches for carrying out our stability study. And we use the most pessimistic batch to determine the shelf life for all future batches. That is, we use the shortest shelf life that's suggested by the 3 batches. So whichever of the 3 indicates the shortest shelf life, we select that as the shelf life that we will use for all future batches. Also, because we only use sample data, it is possible that the regression line which we produce from our sample data would give rise to a shelf life that is too long. And so in order to be conservative, we don't actually use the line itself, but instead we use a confidence interval based on the line. Based on a regression line, we can construct a confidence belt. So we use this confidence bound and we determine the shelf life based on that confidence bound so that we have additional confidence in the shelf life that we have set, because we don't want to set a shelf life that's too long and expose patients to a risk. We use a lower confidence bound because we do know that the active pharmaceutical ingredient can only decrease. We have no expectation that it will increase. So rather than a two-sided confidence interval, we set a 95% lower confidence bound. So here's a graph showing the regression lines for 3 different batches of a drug product, batch 1, 2 and 3. So you'll notice they each have their own regression line based on their own data. And we take the most pessimistic of those, which is the green line, batch number 3 in this data set. So that green line is the one that we will use, batch 3. We will use that to determine the shelf life for all future batches from this process because it indicates a shorter shelf life than the other two batches which we tested. You will notice on the left-hand axis, on the y-axis, assay percent, that we have marked the 90% point and drawn a horizontal dotted line from there. The software does this automatically. So that's the threshold. When the line falls below that threshold, that's when we set the expiry date. And we see that that line reaches the lower confidence bound at just more than 30 months. In fact, the value is shown at the top of the graph, 34.02 months. So that's a suggested shelf life. Now we might choose, if we're choosing between 24 months and 36 months, for this product we'll have to choose 24 because a 36-month shelf life is not supported by the data. Now, because sample sizes used in stability studies are quite small, it sometimes makes sense to pool the data, and we're going to talk about that now over the next number of slides. By using small sample sizes, we could get shelf lives that are unreasonably short, and so it makes sense to combine data from the different batches. So the three batches each provide us with data. Rather than constructing three separate regression equations, perhaps it's possible to combine the information in some way from those three batches. And we call this the pooling of data. Pooling is putting the information together from different samples to give us a better picture of what's going on in the process. So the first step we take in pooling the data is that we pool the mean square error, which is equivalent to pooling the standard deviation. So we assume that the standard deviation is the same for all three regression lines. Now this is a very reasonable assumption because the standard deviation is largely due to the precision of the measurement system which is used to perform the assay. And so that's a very reasonable assumption, and this step is always taken. This is the first step in pooling, and we always take this step. We pool the variance. We pool the mean square error from the different batches. The second step of pooling is a step which may or may not be appropriate to take. And this step of pooling involves making the assumption that the different batches have the same rate of degradation. So we're assuming that the percentage of active pharmaceutical ingredient decreases at the same rate in every batch. Even if one batch began with somewhat more active pharmaceutical ingredient than another, we're assuming that the rate of degradation is the same. That's the equivalent to the null hypothesis, which says there is no batch time interaction. You'll notice that means that the effect of time doesn't depend on the batch. So time affects all the batches in the same way, same rate of degradation. So we test the null hypothesis represented by the batch time interaction, and we test it at the p-value of 25%. Now normally we test hypotheses at the 5% level, and the reason that we're using this higher p-value of 25% is that, again, because it's a pharmaceutical product, we are being very conservative. We don't want to take this step unless the data indicates that it's safe to do so. So testing at a p-value of 0.25, and if the p-value is greater than 0.25, then we can accept that it's reasonable to pool the slopes. So if that null hypothesis is accepted, then we proceed with the second step of pooling, which is that we use the same slope for all three regression equations, but we still allow each batch to have its own intercept, because some batches could have begun with a higher percentage of active than others. And so this is illustrated on this slide here. Notice that this time, while we have three lines, the three lines have the same slope. So we have fit a model where there's a common slope, and each batch then has its own intercept calculated from its own data. And on this occasion, with these data, we've got a shelf life of 41.7 months is suggested by these data. Now, there's a third pooling step, and this assumes that the initial percentage of active pharmaceutical ingredient is the same in all batches. that all the batches began with the same percentage, because often batches will be made and the initial quantity of API might not be 100%, it could be 101 or 99.5% or whatever. So this pooling step assumes that the batches are all the same to begin with. They start out at the same with the same percentage of API. So the null hypothesis says that batch has no effect. So we test the batch null hypothesis. And again, we use the conservative p-value of 0.25. So if the batch p-value is greater than 0.25, then we allow ourselves to take this third pooling step. These pooling steps are taken in sequence. We always begin with the mean square error being pooled. Then we may, if the data allows, proceed to the pooling of slopes. And now we may take the third step if the data allows. And if we reach a suitable shelf life at an earlier pooling step, we don't even bother to proceed to later pooling steps because we already have an adequate shelf life. But we take these steps in sequence if the data allows us to. So if we accept this null hypothesis, then we can say the batches are all the same. They begin with the same quantity of active pharmaceutical ingredient and they degrade at the same rate. So basically, the data from the three batches are all the same. We just have basically a single set of data which we can use to construct a single regression equation. And this procedure, this pooling procedure, is approved by the International Council on Harmonization, the ICH. So this third pooling step leads us to just a simple regression line. All of the data are pooled together to give us this single regression line. And so we can see in this example that's shown here for this product C, these are different products and these different graphs. All the data are used to produce a single regression line, and there's a lower bound, and when that lower bound crosses the 90% threshold, an expiry date is suggested. So here it's 65.79 months. So that's we've just talked about the main material to do with stability studies in order to set expiry dates. But there's a few other issues we'll just mention here now as we bring this section close to a close. We've just looked at a single factor so far. Batch is the only factor along with time. Of course, time is a continuous predictor, a continuous variable, and batch is a categorical predictor. And we have no other factors in the model. But it is possible to include other factors. For example, we could include, along with batch and time, we could include strength. We might have paracetamol tablets that are 500 milligrams and some that are 400 milligrams and some that are 200 milligrams. So we could include strength as yet another factor that may affect degradation and setting of expiry dates. We could also include container size. We could have a large jar or a small jar of product. And it could happen that different expiry dates would be appropriate for the different container sizes. So we sometimes include these extra factors in a stability study. And when we do that, sometimes we do what's called bracketing. That is, if we have multiple container sizes, from smallest to largest, we sometimes use only the very largest and the very smallest. And we carry out our stability study using those container sizes. And then we assume that that expiry date would be suitable for all the intermediate container sizes. We just assume that the expiry dates or the shelf lives for the intermediate containers aren't any shorter than the smallest and largest container size. The other thing we might do is called matrixing. It just means because we have a lot of different strengths and container sizes, we don't necessarily study every different strength and every different container size at every different time point for every batch. Instead, we carry out what's basically a fractional factorial experiment, where we look at a combination of these, but not every possible combination. We can also carry out accelerated stability tests. Because it takes time to carry out a stability study over, let's say, 48 months, we can instead store the drug product at elevated stress conditions, that is raised temperature and raised humidity, which would tend to give rise to shorter shelf lives. And then we can determine what is the shelf life under these advanced stress conditions. And then if we know what the impact of that stress factor is, we can infer then what would the shelf life be under normal recommended storage conditions. Sometimes it can happen that there's a non-linear relationship between the assay percent and time. Like the drug may degrade quickly at the start, but then the rate of degradation might slow down. If that's the case, we can use a data transformation to linearize the relationship. And that is discussed in earlier parts of chapter 6. The response we've talked about so far in a stability study is the percentage of API. And of course, we set the expiry date when that falls below a certain level. But there could be a different concern. We could have a degradation product which is toxic. And if we have some toxic degradation product which increases over time, well, then that may be a greater concern. So we can carry out a stability study in order to ensure that the quantity of some toxic degradation product is below some certain safe threshold. And in that case, of course, we would have an upper specification limit for the highest tolerable amount of that degradation product. And we would use an upper bound on the regression equation. So it's all done in a very similar way. This time, of course, the line would be increasing in slope, increasing from left to right, so the slope will be upwards, and we use an upper bound to make sure that the quantity of degradation product is not higher than what's tolerable. You can read more about this in the textbook in section 7E.